Hello everyone. I would like to share with you today a form finding method I've been working on recently. It consists on form finding a NURBS surface, and it is interesting because it uses only ready available basic Rhino and Grasshopper tools. No need to download anything else. It delivers a single smooth surface, which is ideal to undertake further operations, for instance ideal for a CFD simulation, or to be trimmed easily, or simply for visualization purposes. For example, a conventional finite element software would typically output a discretized faceted surface instead. Thirdly, the modeling time is minimum, yet running time is comparable to other solvers, but for modeling only the boundaries have to be clicked in Rhino. So what we are going to do by defining this perimeter is to enclose a grid of points. At each point the membrane theory is evaluated, and then an optimization algorithm is run to make sure all nodes of the grid meet the stress equation. Grasshopper offers genetic optimization and simulated annealing. The second is used as I found it a bit more efficient for this particular problem. So I will show you a couple of examples of the method and how they compare to the results of a dynamic relaxation solver, which can be considered a benchmark. These are four random curves that will define the perimeter of our structure. They've been defined so that they provide an extreme curvature, but they are completely random. So let's open the script and see what it does. First we have to call these curves in a certain order, so that by doing that we will define the warp and field direction. Let's start by calling it. This is the bottom one, top, left, and this is the right. Okay, we can set number of subdivisions for the internal points, but of course it will make everything slower. We need to define a stress ratio. For this exercise we'll have in field direction 1 kilonewton per meter and in warp direction 2 kilonewtons per meter. No pressure for this one. We'll see another one after this one with some internal inflation, but not in this one. Now at all these points will be evaluated the memory theory. So these are the variables object of my optimization algorithm. They are sliders here in Grasshopper. You can see how they move, alright? Under a certain range, the range defined for this variable must include the final solution. Right. Now the initial shape is completely independent, as in any form finding exercise. We'll just leave them here at constant set value, but any initial shape is valid. So any initial value of the seed coordinate for this point is valid. Now let's run it and see what it does. As I said before, rather than the genetic algorithm, the simulated annealing seems to provide better results. So it's the one that will be run. What I'm seeing here, what I'm monitoring, is the sum of total residuals. This is the object of minimization, which is moving here, and these are all the local residuals that I want to see. So what we will see now on the left is exactly what we see is the nodes bouncing up and down randomly at the beginning, and as soon as it start getting closer to a solution, they will start moving less and the solver cooling down. There is a risk of it getting locking in a local minimum. That is not the good solution. In this case, we can just skip to the next track, or just leave it running for a long time. It will run the optimization many times and save the best solution. Now, some tips to improve and the solution and to make it faster is to have the range of this set value of the variables as small as possible, therefore reducing number of possible combinations. But of course, this needs previous knowledge of how the shape will be. And another option, but it's not recommended, if you want a quick solution, is to reduce number of decimals in this set value. This will also reduce number of combinations and take you to the right solution, but at expenses of having a high residual at the end. So what we can see is that is in the right path. It is providing here a concave curvature, and here in the field direction is a convex shape. So this is what we wanted to do. Now we will stop it for a moment. Don't wait till the end. For the sake of this exercise, and we'll see what it has generated. I'll have to bake it, this surface. And what I will do is to compare a shape that I left running for longer and to converge better. Is not this one, but this one. So I will remove the one that we've done now very quickly. This is the one that I left running before longer and to converge better. And now we can compare this one with the solution given by dynamic relaxation solver, the best in this planet, which is inTENS by Tensys. And what this would provide is this shape, and we can see that they match really good. The elevation profile is almost perfect, and the shape it has generated is really good. Bear in mind that because of the spline nature of our surface, the accuracy by only having 6 internal nodes is not that bad, and it has generated a reasonably close 3D shape. Alright, now I'll show you another example. I'm not going through the process again, but show you the results of another example where I had inflation pressure. Is an example where there is well, let's switch it on. This shape, it has 2 kilonewtons per meter in field direction, 6 kilonewtons per meter in warp direction, and an inflation of 1 kilopascal. Okay, and this is the shape it generates. Now when we compare with the finite element model, this is what it does. Again, in a side view, we see is very in good agreement. On an elevation, here it was hard to match. The side, it was really difficult because it's inflating sideways. We don't have enough internal points to do that. But I'm quite happy that looks good enough for what it's able to do, and it's an extreme shape. So that's all from me. Thank you very much.